Good evening. I'm Sunita John, and thank you for joining us today at this meetup. We are happy to have you with us. As we all know, the Neural Information Processing Systems, abbreviated as NeurIPS, is a machine learning and computational neuroscience conference held every December. The 34th annual conference was held last week from December 6th through December 12th. NeurIPS encourages meetups across countries in the world as a community building activity and to share the excellent sessions from the conference with the rest of the world. And we are glad to host the first India NeurIPS meetup. We hope you will enjoy this session. For our meetup today, we have 5 distinguished Indian speakers who are AI experts in their own right, and a NeurIPS session by a stalwart in research, Dr. Meetup Bell. Our first speaker for today is Dr. Jaya Nair. Dr. Jaya Nair is Associate Professor at IIIT Bangalore. Professor Nair obtained her PhD in computer science from the University of California, Davis, after a BTech in aerospace engineering from IIT Madras, and an MS in computational engineering from the Mississippi State University. Her areas of interest are visualization, scientific computing, computer graphics, and computational geometry. She leads the Graphics Computing Lab at IIIT Bangalore. She is also the core member of the eHealth Research Center at IITB. Welcome, Dr. Jaya Nair, and it is over to you.
Going to give a talk on the hierarchical organization of functional segregation of the brain. I am Jaya Srivalsan Nair, a faculty member at the IIIT Bangalore. Today I will be giving the talk on functional connectivity brain network analysis, which is part of the PhD thesis work by Reddy Rani Vangimala under my supervision. We are part of the Graphics Visualization Computing Lab and the eHealth Research Center at IIIT Bangalore. In today's talk, we will cover 3 key phrases: brain networks, functional segregation, and hierarchical organization, and then talk about a proposed approach for functional segregation using exploratory factor analysis. The brain of human as well as other organisms can be studied using approaches borrowed from network science. What is really needed is to construct networks based on different aspects of the brain. Let's look at how a typical workflow for brain studies using networks would look like. The starting point for the network construction is the measurements taken using non-invasive techniques as shown in the first row. Common examples of networks that are generated are in the middle row, which include transcriptome and interactome, connectomes, networks of functional and effective connectivity, and social networks. Bottom row shows the common mathematical framework one would use using graph theory and network science for the analysis of the networks. Let's now take a moment at the second row. To construct the brain networks, the brain volume is first discretized to regions of interest. Then one goes about studying the interactions between these different regions. Thus, these interactions become the edges and the regions of interest become the nodes of the network. This line of study has been around for 2 to 3 decades now, and the research community is working on fine-tuning the methods for complex problems of differential behavior, say in the presence of brain disorders like Alzheimer's, autism, etc., or how the brain would change with age, etc. While the application space is rich with relatable problems, the methodology space looks at network analysis using different data mining methods. From what we know of the brain, the subset of the spatially contiguous regions of the brain work together, both structurally as well as functionally. The difference between the structural and functional organization of the brain spurs the need to study them separately and then again together. Let's first talk about the nodes in the brain network. The brain anatomy is divided into different spatially contiguous regions of interest using a parcellation atlas. This parcellation refers to dividing the spatially continuous cortical manifold into homogeneous and unique regions. We can have several parcellation atlases which comply with both structure, that is the plumbing, and its functionality. So examples are AL, DOS, HOA, Schaefer. We see in A in the image that the network nodes could be defined at different scales. The macro scale of millimeter resolution is for the parcellations. It can be refined to neuronal populations, which is the mesoscopic scale at hundreds of micrometer resolution. It can also be further refined to neurons, which is at microscopic scale at micrometer resolution. That is, taking one neuron at a time. Let's now talk about the edges in the network. Depending on the non invasive measurements used for generating values for the interactions, we can have different kinds of networks. That is, structural, functional, and effective connectivity networks. Now, the classification is based on the type of edges in the network. Structural network gives the anatomical connections measured using diffusion MRI. Functional connectivity is provided by the undirected statistical dependencies obtained from the blood oxygen level dependent, that's the bold signals from the functional MRI, fMRI, in different working states. That is, one is resting state where the subject is not doing any task, or when the subject is doing specific tasks. The effective connectivity is the influence of a node, which is the neuronal population, with a similar node. In the context of causal dynamics measured using bold or EEG or MEG signals. The effective connectivity gives the directed causal relationships among the distributed responses to a task. Hence, it is important for the full understanding of the functional integration that we use neuronal coupling and effective network analysis. We see this in image B. Just for the sake of completeness, we will also mention about the time scales involved in these networks, in addition to the spatial scales. In terms of time scales, we see that functional networks can be recovered from long windows of neuronal activity, which is in minutes, overlapping with the underlying structural network. However, the sequence of networks recovered from consecutive, shorter uh, time windows in seconds show significant fluctuations in functional topology. At zero point 0.1 seconds, we also see intermittent synchronization and desynchronization between brain regions. Now, we look at this vast body of connectome networks, which is of interest to us. These refer to the connectivity networks that we have already talked about and include both structural and functional networks. The structural connectivity is fixed and underlies cognition and behavior, while the functional connectivity is dynamic and found to be self-organizing. These connectivity networks have several similarities but also have several dissimilarities. Now, the divergence between the function and the structure is where the brain study becomes very interesting. Now, the structural connectivity network has been widely studied more than the functional connectivity network. So, our focus here is on the static analysis of the functional connectivity. It has been observed that the functionally related regions in the brain tend to have very high density of connectivity, which is synonymous to a community in the network science. Functional segregation refers to neuronal processing carried out amongst these communities. Now, these communities are defined by dense intra-community connections but sparse inter-community connections. Now, this arrangement of connections falls in the category of small world networks in the network theory. It has been found that there is statistical dependence of neural signals within these modules or communities and statistical independence between the modules or communities. Now, this promotes what we call as functional segregation. Now, let's take a look at functional integration. Functional integration means that the communication between the communities are made economical. Now, this happens through the use of hubs and the dense interconnections between hubs, which are called rich clubs. Now, the interesting part to note here is that the structural connectivity network has very similar hierarchical modular organization, similar to the functional connectivity network. Now, talking of the hierarchical organization, here what we mean is that the communities at a very high level can further be decomposed to smaller communities, thus having nested communities. Now, hierarchy provides near decomposability, which makes a simple system a complex system, and that makes the system more adaptive. Decomposability provides stable intermediate forms to help adapt one module of the system at a time without the risk of loss of function in other already adapted modules. This is seen in biology again and again. We see in the figure here that there are 5 major modules of the functional brain, but we also see that the distribution of the submodules is not uniform and not spatially contiguous, as we can see in the central image here. The medial occipital module has no major submodules, but the frontotemporal module has several submodules. Now, the hierarchical organization throws a curveball. In a network with an intrinsic hierarchical structure, finding a single partition solution is now no longer valid. And this becomes a problem as the number of partitions is correct no matter where you take from which hierarchical level. One of the solutions to this problem is to use multi-scale approaches again to provide the flexibility of finding any number of partitioning and figure out an appropriate way to aggregate these results, for example, using consensus votes. Thus, the hierarchical organization of the functional segregation is key to the work that we are doing on community detection in functional networks. Now, let's take a look at the conventional method of community detection in functional connectivity network. We already said that the functional connectivity network is a completely connected graph because it's a correlation matrix. Now, we first remove insignificant edges in this fully connected network and then perform community detection in the edge filtered network using conventional methods such as Louvain community detection, InfoMap, etc. Now, it becomes important to find an appropriate threshold for filtering because that influences the result. However, the problem we face with the choice of threshold is that minor perturbations in the threshold leads to uh, topological changes in the network. For our case study of a 90-node network with AL parcellation, we observe that we get 5 communities when we use zero point 0.4 as a threshold for edge weight. We get 6 communities when we use 0.45 as a threshold, and we get 7 communities when we use zero point 0.5 as a threshold. In the image here, we show that the communities cause drastic changes in the network topology, as can be seen using different graph layouts. So in A, we show the force directed layout. In B, we show the circular layout. And in C, we show the hybrid matrix layout, which is used for specifically small world networks. Now, what we are trying to do here is we look at if we can exploit the semantics of the correlation matrix as an alternative for finding communities in the functional connectivity network instead of going down the path of network analysis after edge filtering. So we use this statistical method namely the exploratory factor analysis for functional segregation. Now the idea here is to use the entire correlation matrix as is without filtering. We are working with a fully connected weighted network here. We shift our focus from solving the community detection in brain networks using network science methods to finding groups of nodes correlated to a factor using factor analysis, which is conventionally done on a correlation matrix. Now, let's take a look at exploratory factor analysis or EFA. It's a statistical method that's used for finding factors amongst intercorrelated variables. Factors are patterns describing the basic structure of a domain. So the empirical knowledge of the existence of a causal model determines the causal labels for the factors. in such a way that these factors are just purely classificatory or descriptive. In factor analysis, each random variable is then expressed as a linear combination of factors. Now let's take a look at how it will work for the functional connectivity network. Here we assume the nodes are random variables which are intercorrelated, and then we find the nodes which are affiliated with each factor based on the factor loadings. The factor loadings are the values which say how these nodes are affiliated to the factors. Now thus we find groups of nodes which is synonymous to the communities in the network. Now, EFA has been heavily used in psychological and personality testing. As an example, here we show how 9 different cognitive variables used for Thurston personality schedule, which is a personality test, uses EFA on the correlation values for the variables in the test. And this yields 3 different unique factors. Now, for the implementation of EFA, the number of factors becomes critical. It is expected as an input, which is indeed a problem here. Given the hierarchical organization of the functional modules, we are no longer able to provide a definite number as an input to the EFA. So there is no notion of a ground truth here. Hence, we now consider the number of factors as a scale and then use a solution of multi-scale approach to now perform functional segregation. Now, EFA is known to have its own problems with replicating and generalizing results. In our workflow, we fix specific rules to implement EFA with a predefined number of factors as scale. We then implement multiple runs across different scales. We aggregate these runs by creating something called the Coassociation Matrix. The Coassociation Matrix consists of the same set of nodes but now with different edge weights. The edge weights now give the value for the likelihood for any two nodes to have been in the same community across different scales that we have done the runs for. Now, this co-association matrix is essentially a transformed network. It is a weighted, undirected network where we can now find communities using generalized low-gain community detection algorithm. So we have a weighted, undirected network where we find communities using a conventional community detection algorithm. So what we have done here is to use the correlation values to determine which are the nodes which can possibly be caused by the same factor in causality analysis. Now let's take a look at the functional segregation results which we have gotten after selecting the best multi-scale EFA in an ensemble. Now for a case study here, we have used a 19-node functional connectivity network from an AAL parcellation, which is built from 198 healthy right-handed volunteers in the age group of 18 to 26 years in resting state, awake with eyes closed, and of which 122 are female. Now, this data set is available with the BrainNet Viewer tool. The visualization of the 5 modules that we have gotten from running multi-scale EFA is now done on the brain surface, as you can see. We clearly observe hemispherical symmetry in this case study. We also see that modules we have gotten align with the 5 known largest subnetworks in the functional connectivity. These modules are motor and auditory regions, default mode network, limbic and subcortical areas, visual processing region, and attention processing region. Now we see these diagrams which are called alluvial diagrams or Sankey plots. These are flow maps between sets. Now these diagrams can be used effectively to observe differences in constitution of different sets. Now we'll use this to study the changes in the partitioning. When we use our method versus hierarchical consensus clustering method, which is the state of the art for functional connectivity network and its community detection. The left plot shows that we do not have much difference from the state of the art result. The plot on the right, on the other hand, shows us that we see hierarchical decomposition of the network, specifically in this particular case study, where when we increase the number of factors and perform a single scale EFA on the network, we see that each module decomposes to submodules. Now, this is a good observation that complies with the expected hierarchical organization of the brain. Now, let me conclude my talk here after we have talked about a lot of important concepts. The network science provides tools and techniques to understand connectivities in the brain and its dynamical behavior. The static representation of the brain networks is still an incomplete picture, but the brain networks change dynamically and it has to be studied as such. However, studying the static analysis is essential for understanding the dynamical behavior. There are different types of connectivities in the brain. They are the structural, functional, and the effective connectivities. Now, we also looked at functional segregation and integration and hierarchical organization, which are key aspects of the interactivity between different regions of interest in the brain. Functional segregation is needed to distribute the response to a task or resting state to the different parts of the brain. And integration helps in the economy of communication between these different modules which we got from functional segregation. The hierarchy now allows for stable intermediate forms of a complex system, which gives us the key challenge of not having the ground truth for the number of partitions. Unlike structural connectivity, functional connectivity is studied using Pearson's correlation, and hence we can use exploratory factor analysis for our work. So our proposed method has given very good results for our case study. We thank you for your attention and we hope we have conveyed salient information about brain functional connectivity networks. We take this opportunity to also thank the Ministry of Electronics and IT, Government of India, for their generous PhD fellowship through the Vishwesvaraya PhD scheme that supported this work. We can be reached at the email addresses and URLs given in the box on the right. We thank you all once again.
Our next speaker is Dr. Shanti Medesani, Director of Engineering at Matworks. He leads the Autonomous Systems and Sensor Processing Group in Hyderabad. His research interests include autonomous vehicles, computer vision, machine learning, pattern recognition, sensor processing, and robotics. Dr. Shanti has over 55 issued patents and over 100 reviewed and invited journal and conference publications. He is a senior member of IEEE and holds a PhD in computer engineering and computer science from University of Missouri, Columbia. Welcome, Dr. Shanti Medesani, and it is over to you.
Hi, welcome to the talk on applications of recent advances in deep learning technologies. I'm Shanti Medesani, Director of Engineering at Mathworks. My team in Hyderabad is focused on autonomous systems and sensor processing. Now, we're all aware that deep learning is a key technology driving the current artificial intelligence megatrend. Popular consumer applications of deep learning are numerous, and they include speech recognition in smart speakers, face detection in cameras and phones, and autonomous self-driving vehicles. Recent advances in deep learning have been primarily focused on getting models to work with less data, fewer labels, and parameters. Domain experts, on the other hand, wish to leverage the rapidly evolving DL research, use domain-specific reference applications, but they may often lack the DL expertise or the time required to build such high-performance models. Now, the Mathworks ecosystem, including Matlab, Simulink, and a wide array of domain-specific toolboxes, help bridge that gap and makes robust AI models accessible to the field experts. Now, let's look at a few of these recent advancements and how they can be applied to domain-specialized workflows. Generative adversarial networks, GANs. These are getting quite popular. GANs are an approach to generative modeling using convolutional neural networks. Generative models discover the underlying patterns, correlations, and distribution of the input data so it can generate newer examples, synthetic examples, that could have come from that same input data distribution. So GANs use two submodels, a generator and a discriminator. These two submodels compete with each other as adversaries, and hence the name, and they produce a generative model. The generative model is then used to generate plausible examples very similar to the input. Now, you can use GANs for determining real versus fake or synthesizing one class of imagery by using another class of imagery as input. We will see some examples in the coming slides. Here is an unsupervised GAN network called UNIT. It stands for Unsupervised Image-to-Image Translation. UNIT can be used for both image analysis and synthesis. A unit is a fairly complex network. It involves 6 subnetworks, encoder decoder blocks, that help learn the domain mapping between a source class of imagery and a desired target class of imagery. Now, such networks can easily be built with Matlab. Our dedicated APIs allow user to control the parameters to achieve the desired training impact, and in turn, use the trained network for prediction. Here is an application of unit GAN for image synthesis. So in this case, we have two domains of imagery. One is the dusk category and the other the day category. Our goal is to train the GAN so given a dusk image, we can generate a corresponding realistic day image. Now, this would be very helpful for simulation of different environment conditions for testing autonomous vehicles or for homologation tasks. Now, using images from both classes of imagery as the input-output pair, we can train this unit GAN and in turn use it to predict corresponding day images for any input dusk image or vice versa. Now, for the results shown here, the network was trained with 400 odd images, and there were no temporal information queues leveraged. And you can see that the network is able to produce consistent results for both day to dusk and dusk to day transformations. You can also see that the results look visually consistent and the approach works well even on unseen but similar looking input data. Here is another example. In this case, the unit GAN is being applied to tomography. So low dose injected scan images of tissue are used as the input here to generate the corresponding high dose tissue scan imagery, like the image shown in the middle. Now, high dose is harmful to the patient, and this technique learns to predict the response of the patient to higher dosage without actually injecting that dosage level. Now, it does this by learning to extrapolate from the low dosage imagery to generate the high dosage patterns. So that was unit GAN, and that allows us to go from one class of imagery to another class of imagery in an unsupervised form. Another popular GAN is Pix-to-Pix HD. Some of you may have heard of it. It was originally designed for synthesizing images from pixel label maps, as shown on the left here. So you provide a label map as input and you get a synthesized scene as output. So the Pix-to-Pix HD GAN is able to synthesize an image that corresponds to the different labels in the map, such as a pole, a car, people, sidewalk, road, etc. Now, all of that structure and detail is captured in the synthesized scene. Matworks provides useful APIs to build, train, and test this network. Users can modify and adapt the network to suit their synthesis needs. In this video, we're showing a labeled scene on the left and the corresponding synthesized imagery on the right using the Pix-to-Pix HD model. Now, only 500 training samples, and by training images, I mean a pair, a label map that you see on the left and the corresponding real-world image that you see on the right. Using 500 such pairs, we are able to generate this synthesized result. Now we can see that it is already able to see the structure, place objects in the right locations, and construct a scene. The results, of course, improved significantly if we use more data. Here are results using 5,000 training samples. The results show the synthesized imagery and the original image from which the label map was generated. So on the bottom right is the synthesized imagery. The bottom left is the original captured scene from which the label map on the top was generated. So given the label map as input to Pix-to-Pix HD, it produces the bottom right image. And you can see that it is quite realistic. Now it also happens to be a variation of the bottom left image. So it is a nice way to produce variations of an input class of images. Here is another interesting GAN, the AdaptSeg GAN. Now this operates in a semi-supervised fashion where data from simulation engines is leveraged to do semantic segmentation. Now, of course, for simulation engine data, we also have the ground truth available for the different objects in the scene. So the AdaptSeg GAN learns to do semantic segmentation on synthetic imagery. Once that training is mature, we use transfer learning to adapt this network to work well on real-world data as well. But here we use a relatively small real-world data set. So the end result is a GAN that has predominantly been trained on synthetic data, but can effectively be used to semantically segment real-world data as well. So here are results of using the AdaptSeg GAN. The video shows incremental improvement of road object segmentation as we add more real data to the transfer learning stage. From the video, you can see that as we increase the amount of real-world data used in the transfer learning stage, we can get more and more improved results. Matlab provides off-the-shelf training and inference interfaces for popular object detectors like YOLO v2 and v3, and also pre-trained models are available for faster training using transfer learning. In addition to object detectors, we also have task-specific models for typical computer vision tasks like face or pose detection. Okay, so that was for image and video processing, but about other sensor modalities. Here are networks for processing terrestrial and aerial LiDAR data. The top left video, we show object detection workflow using point pillars. It's a popular network for point cloud processing, and you can use it for car and truck detection. The top right video shows semantic segmentation workflow for LiDAR point clouds. And this result segments the data into 14 object classes, and it uses the Salsa Next model. The bottom image shows how PointNet++ network is applied for semantic segmentation of aerial LiDAR data captured from aerial platforms. So customers can leverage our tools in multiple domains. We have many sizable investments going on here. We have several examples that teach customers how to use the shipped networks in many different kinds of applications. They could use audio, LiDAR, radar, wireless, and others. And we have many more in the pipeline too. These span computer vision, signal processing, the medical domain, finance, use of reinforcement learning, and so on. So our goal is to on-ramp customers with AI in all the markets we serve. The broader deep learning community, in which you're all a part of, is incredibly active and prolific, and new models are coming out all the time. Because we support the Onyx standard, you will have access to those new models and can easily work with them by importing them into the Matlab environment. We're also working on a TensorFlow 2.0 importer. Now for deployment, which I presume is of deep interest to you, our unique code generation framework allows models developed in Matlab to be deployed anywhere without you having to rewrite the original model in the corresponding native code. This gives you the ability to test once and deploy the entire system many times and not just the model itself. Matlab can generate native optimized code for multiple frameworks, and it gives you the flexibility to deploy to, say, a lightweight, low power embedded device, or a low cost rapid prototyping board, or an edge based IoT application platform. Here are some new and critical areas that need more research across the community. We are investing in verification and validation for AI to help support these new explorations. These range from being able to explain the decisions being made by the network, the coverage of the neurons in making these decisions, the robustness of the predictions against adversarial inputs, or say partially occluded inputs, and lastly, being able to trust these predictions. So in summary, Mathworks offers tools that help customers leverage the latest advances in the field to enable end-to-end deep learning workflows. The convenient interfaces we offer help domain experts as well as casual users to leverage these advanced deep learning algorithms. Reference workflows for several different domains are covered in our toolboxes. Lastly, our ecosystem of tools enables both data synthesis as well as data analysis. Thank you for listening.
Thank you, Dr. Shanti Medisani. Our next speaker is Dr. Lavanya Tikkumala, a machine learning scientist and an entrepreneur. She holds a PhD in machine learning from the Indian Institute of Science and a master's in computer graphics from the University of Utah. She is the founder of AI Phonic Labs that focuses on AI-based assessments and data science interview prep. Her research has been in the area of Bayesian modeling and probabilistic graphical models. She is the author of several peer-reviewed papers in top conferences and journals and has served in the program committee of several international conferences. Welcome, Dr. Lavanya, and it is over to you.
Hello everyone. Thank you for the slot at NIPS India Meetup. So most of the talks here would be about building new models using sophisticated techniques. So I thought I will instead talk about some of the challenges productizing machine learning models. So a little bit about me, just to add on to the introduction. I'm a PhD in machine learning, and I've been in the industry for a while. But I've also I've initially been a developer, then I've been a data scientist, and most recently I've been on the side of product. So I wanted to put forth some views on how machine learning models can be productized, what are the different steps involved, and what are some challenges. So in this process today, I'm going to talk about the machine learning product development lifecycle. So before that, just for some context, for those who are not into ML who are listening to this talk, in the traditional programming, you give some input and you give a program. The computer does some computation and you get some results. But if you look at the machine learning paradigm, you give some input and you give the desired result, which is like the data, examples to learn from. There's some computation and out comes the program, which is the model. So you see that there is some kind of reversal in paradigm. And what this means is the kind of risks involved are different, since the ML product lifecycle is not as deterministic as that of the regular product. Uh, for instance, the output you get is really the model that you get is really dependent on the kind of data that you give as input, garbage in and garbage out. So if the data is not representative of what you're trying to fit, when you actually look at real data on which you're applying your model to, you're not going to get great outcomes, business outcomes from this model. So the whole point is, how do we actually do this entire process in a way that we minimize these risks? Is going to be the focus of this talk when I talk about the machine learning product development lifecycle. To set some context, let us quickly recap the software development lifecycle, where there is some requirement analysis, or before that, there's of course the problem definition, and then there's design, where you come up with the architecture for the software, and then the implementation, and then testing, and then iterating it to see whether going back and repeating the whole process, right? Now here is a slightly more detailed view of the machine learning product development lifecycle, because that's what we want to talk about. And the first thing that we note here is that this is also a very iterative process, and there are like all these interconnections. And once again, this is just like one view of it. There could be so many variations, but it is a view to talk about some of the key things that are involved. So in the center, as we see, is the customer or the customer problem definition and the business problem definition, which is like the problem definition phase. And then we have the green box, which is all the initial data gathering, the EDA and literature survey and so on. And then we have the purple box, which is the development of model and the data pipeline and offline and online evaluation. And finally, we have the blue box, which is the rollout phase. And what we see is that there is a gating criterion between each of these. So only when you go through the gating criterion and actually going to the next stage. And the purpose of that is to actually reduce the risk involved in getting the kind of business outcomes that we want to. So now let's dig deeper and understand each of these things a bit more. And before going there, here are some of the typical stakeholders in typical team comprising of product engineering and data science. So usually the stakeholders are product manager, the engineering manager, and a machine learning scientist, a data engineer, an architect, software development engineer, and so on. So sometimes these roles could all not be so distinct. The same person could be handling multiple of them, or in a bigger organization, you could have all these roles. Okay, so let's come to the first part of it, the problem definition or the problem identification. So the goal of the problem identification step is to identify the problem that is impacting the business problem, and also the customer problem, because it's always good to think from the customer point of view. So how is the customer experience impacted? So that's always a good question to ask by making this particular change or solving this problem. Is this problem a bottleneck? So it's very important to solve the right problems. Can I see a potentially significant increase in revenue if I solve this problem? Can I see potentially high efficiency improvement if I solve this problem? So these are different ways of making this more concrete. And finally, it's very important to see what is the dollar value of solving this problem. So that's always a very useful thing to see. And there could be other things like, is solving the problem leading to a competitive advantage? And this is something that usually the product team owns more than the data science team. And one of the outcomes of this step should be to clearly identify metrics to define success, which all the teams will abide by through the rest of the process. So an example could be increase revenue by X basis points for a particular category, or reduce time to ship by X hours on an average. So this is an example of the problem identification step. And the outcome is again, the problem itself and clear metrics to define success. So what are the risks involved in problem identification? So I'm just going through this exercise in a lot of detail for one of these steps and might not go as much in detail for the remaining steps. So the risks involved could be, is this problem going to disappear in a while, for instance? Am I picking the right problem is a very important question. So the risk could be the problem is just going to disappear after a while. It's a temporary problem. Or is another big company going to commoditize the solution to this problem, right? Or does solving the problem actually give competitive advantage, revenue impact? So it's possible that I do this and I do not get the kind of revenue impact that I want. That's a risk. So these are the things that could go wrong. And again, like we said, the outcome is a well-defined problem and success metrics. And typically people come up with like a 1-pager or a 2-pager artifact to document this. And of course, the product team is the main owner of this process. So let me take a small example. I won't take a lot of time here, just to make this more concrete. So this is one of the problems I had worked on in the past, which is product size recommendation in fashion e-commerce, where the problem is that customers were not able to choose the right size online and hence were returning a lot of items. So the idea was, how do you recommend the right size to the customer for a particular product? So in this particular problem, what is the customer problem? The customer problem is that it's hard to choose the size online. The business problem is that there are too many size related returns, for instance, and it could also, which is impacting the total revenue that you're getting, and it could also impact the customer experience, so poor customer experience, right? But the number of size related returns causing a specific revenue impact is like a clear business problem. What are the success metrics here? The success metrics could be like, are we increasing revenue? Are we reducing returns? So these are examples of success metrics, right? So this is usually the first step to the machine learning product lifecycle, defining the problem itself. So now a very important thing to ask at this point is, can this problem be solved without machine learning? Because it turns out that a lot of problems can actually be solved in a simpler way. Maybe they do not give you as much of a boost as you expect, but they can be used to solve it well enough to get started with. And then you can iterate to maybe put more ML in the next step. Once all your processes are defined, once the rest of the engineering infrastructure is in place, maybe you can add ML layer to it. So a lot of times that makes more sense than approaching something as a full-fledged machine learning problem, right? So this is a very important question to ask. And when you come back to this product development lifecycle, that's what you see here. So do I need machine learning to solve this problem? And if the answer is yes, then the next step would be the green box, which is do some initial EDA, first gather the data and do some EDA and figure out what you want to do. But if the answer is no, you might want to solve it in other ways first. Okay, so the next step is the this green box, which comprises of the EDA, data gathering, and so on. So here you want to do two things. One is figure out what data you have and what data roughly you need to solve this problem, and maybe think of get some small subset of the data maybe in order to figure out whether you can you have the right things to what you can do with the data, right? And then the next step is to do exploratory data analysis to understand this data better, and then you want to think of what are the different kinds of things you can do with this data to solve the particular problem. So this could be like various models that can be used. And once again, you also want to do literature survey, which is go and see what others have done typically to solve this problem. So this is again like a very iterative process. You see that each of the boxes, you have like a very iterative process where you might want to experiment, think of some models and realize that you need more data for, you need more label data for some model. So you figure out how to get label data, right? So you might want to get other sources of data, think of other sources of data depending on what you can model. Then you try to get a small sample data and explore the data more to see if what you thought was possible, and so on, right? And you keep iterating. So at this point, one very useful thing to do is to build a strawman model. So what is the very simplest thing you can build? A very simple ML model, or sometimes a non-ML model, which can serve as a baseline for one. And this actually makes things more concrete and clear, and will usually give you an intuition on what is missing and in terms of data, and also whether you are likely to make some kind of an impact in terms of improving your metrics overall, whether you are going to move it in the right direction. So one thing to note in general is to make models as simple as you can. At least to begin with, you want to come up with something simpler. So you make it as simple as you can, but no simpler. For example, if you see that you have a data set, you're trying to do some classification, you have like a very complex nonlinear decision boundary, you don't want to just use some logistic regression, right? So you might want to use a deeper model. But it's important to think of simple models first if they can solve the problem. So that's the green box. The next is feasibility and impact analysis. At this point, you want to determine whether the effort that is involved in terms of the developer and data scientist cycles, in terms of developing the model itself, the data pipeline for the model, and also the final software architecture for serving the model, whatever the other development effort is required, whether it is all worth the amount of impact that it's going to make. So once again, it's really hard to come up with how much impact the model is going to make without actually implementing things, but that's where implementing a strawman model helps often. So once you decide to go ahead with this effort, the next step is the model and data pipeline development. So the engineering effort and the data science team developing the models should actually just go hand in hand, and both should be developed parallelly. And once you have some model that has been built, the next thing to do is offline model evaluation, where what you end up doing is figuring out how your model is doing. So here you need to measure the right metrics. So to create real impact, it is very important to measure the right metrics. So why do I want to stress on this point here? Let's take the example of this product size recommendation problem. So let's think of it as, let's say it's a classification problem. Maybe it's not, maybe it's more complex. Let's say it's you have you're doing a classification problem, and the kind of metrics that you can measure are typically the AUC, F1 score, and so on. So usually data scientists are very comfortable with these metrics, and you need to have these kind of metrics in order to do hyperparameter tuning and to figure out the right model for model selection. But these metrics might not be enough to determine whether your model will have the right impact. For instance, in this case, maybe I could say the ML algorithm level metrics are the AUC and the F1 score, while the problem level metrics could be like the accuracy and the coverage. So I want to make sure that I show the right size, recommend the right size. But if I'm not confident about recommending the right size, maybe I do not want to recommend the size at all, right? So that might be an aspect of this problem. In that case, in how many cases am I able to recommend size? And in those, what is my rate of accuracy? So these might be important for me. And a business level metric could be to measure the revenue increase over a period of time, or think of the number of returns. Now, it is really hard to measure these business metrics unless you actually put this problem in production. So what do? Usually, one way to deal with it is to try to simulate these business metrics as closely as one can. So for example, can I try to, sort of simulate the process to see how many returns would happen if I actually use this algorithm on my test data, right? So maybe whenever I don't predict accurately, let's assume it's a return, and how many returns happen. So that could be like a simplistic thing, but the idea is, can I actually come up with some business level metrics that proxy metrics maybe, but some business level metrics at this stage, which can tell me what direction things are moving in. And sometimes it's very interesting to note that even though we get like very good ML metrics, it might not translate into good business metrics. So that's the reason we want to be careful here. Okay, so once we actually go and do the offline evaluation, in theory, there's no difference between theory and practice, while in practice there is. So we might think that things are going well, but once we put things in production, there are always edge cases that we have not handled, or we might see that the actual data is different from the kind of data we have. So online testing involves some kind of A/B testing, perhaps, to test on a small segment of the population at least, the entire thing that you have built end to end, and see how it works from all different angles, right? So you can actually measure the business metrics directly over a period of time. So if you do A/B tests, you can actually try to measure, like in the case of the shoes, for instance, in the case of the product size recommendation, for instance, you can measure how many returns were there, what was the revenue impact, and so on. And of course, adhering to all the different constraints and things that you need to take care of when you do A/B tests. So coming back to this particular, coming back to the product development lifecycle, once you do online testing, you actually have some numbers to say whether you have the kind of impact you wanted or not. So this is the live impact analysis phase. And if the impact is what you wanted, you would actually go back and roll out the model. If not, you would go back, of course, and refine the problem, either change the success metrics that you had, maybe be okay with like a lower level of lower improvement, or lower metrics, or you might actually change the problem itself. So you can actually iterate here. So but once you determine that the impact is the kind of impact you want, you'll go to the rollout step. So the rollout step involves rolling the model out to a larger population. So typically it could be like different geographies or different categories and so on. And at this point, you might come up with problems that are specific to, so you probably tested extensively on one category. And so maybe for the product size recommendation, you probably, tested it on one kind of apparel, like jeans first. And then when you actually roll it out for t-shirts, it might be like totally different, right? And you would come up with all these problems, but they need to be ironed out. And then if things work out, you would actually roll it to different categories and different geographies, right? Again, here it's another aspect here is to make sure that you have the data pipeline ops and maintenance. So what we mean here is we need to actually define who owns what part of the code. If something goes wrong, who is going to fix it, define proper SLAs, define proper ticketing system or whatever support system for your software, and these things need to be taken into account from a maintenance perspective. And at this point, it might be a good idea to think of, what are the next things you want to do. So another aspect here is to make sure that you have all the monitoring in place and all the logs and various other support you need to debug production issues in place, and so on. So this was the machine learning product development lifecycle. This is a short talk, so could not go into a lot of detail with real examples on many of these things. But let me repeat the key takeaways here. The key takeaways are that building products using ML is a very iterative process, and you want to do it in a way that minimizes the risks involved. So to make models for products, we want to make models for products as simple as we can ideally, but no simpler. And to create real impact, it is important for us to measure the right metrics. And this will definitely reduce the risk when we actually roll out the product. So that's all for now. Thank you.
Thank you, Dr. Lavanya. We will now share the NeurIPS expert session by Dr. Muinatu Bell. Dr. Muinatu Bell is an assistant professor of electrical and computer engineering, biomedical engineering, and computer science at Johns Hopkins University, where she founded and directs the Photoacoustic and Ultrasonic Systems Engineering Lab. Dr. Bell earned a BS degree in mechanical engineering from Massachusetts Institute of Technology, received a PhD degree in biomedical engineering from Duke University, conducted research abroad as a Whitaker International Fellow at the Institute of Cancer Research and Royal Marsden Hospital in the United Kingdoms, and completed a postdoctoral fellowship with the Engineering Research Center for Computer Integrated Surgical Systems and Technology at Johns Hopkins University. Dr. Bell is a recipient of multiple awards and honors, including MIT Technology Reviewers Innovator Under 35 Award, the NSF Career Award, the NIH Trailblazer Award, the Alfred P. Sloan Research Fellowship, the Ora Ralph E. Povey Junior Faculty Enhancement Award, and Maryland's Outstanding Young Engineer Award. She most recently received the inaugural IEEE UFFC Star Ambassador Lectureship Award from her IEEE Society. We will now listen to Dr. Bell's interesting session on ultrasound image formation in the deep learning age. Welcome, Dr. Bell, and it is over to you.
Hello, my name is Muinat Bell, and I thank the chairs for inviting me. It is my pleasure to deliver this keynote presentation on the topic of ultrasound image formation in the deep learning age. Many of us are familiar with ultrasound. It's ubiquitous in the clinic. This is a This is a standard clinical setup showing a sonographer holding an ultrasound probe and viewing an ultrasound image on the screen. The first medical ultrasound image was created in the 1950s, and in the 60-year history of ultrasound, the signal processing methods used to display the images that sonographers see on the screen with this setup have fundamentally remained the same, in that they all rely on the fundamental beamforming process to make images. By the end of this talk, I hope to provide you with a better appreciation of the ultrasound image formation process, starting with raw data. From this raw data, we create the images that sonographers see on the screen after passing through the beamforming process. This beamformed image can then be used to segment structures of interest. Deep learning has traditionally been applied to beamformed images to segment structures of interest, but what we're doing in my lab that's new and different is we're starting with the raw data and replacing the mathematical component of image formation with deep learning to produce more interpretable images. As I mentioned, ultrasound is ubiquitous throughout the clinic. It can image many anatomical structures as shown here, and there are many benefits that make ultrasound a big player in the world of available medical imaging options. For example, ultrasound is safe and portable. It can provide real-time information and it's cost-effective, and it ultimately provides useful information for both diagnostic and surgical cases. However, ultrasound imaging does suffer from several outstanding challenges that have persisted in the 60-year history of the technology. These challenges include that ultrasound images are typically known to be noisy, to contain a granular texture appearance known as speckle, to contain acoustic clutter, which causes regions that should appear black to appear as if they have signal within them, as well as challenged by sound attenuation at deeper depths, making it difficult to see deep structures, and poor resolution at depth, making it difficult to resolve structures that are deep within the body. Ultimately, these challenges make it difficult to segment structures of interest, as well as difficult to generally interpret images. At the heart of these challenges is basically the idea that ultrasound images have poor quality. With this understanding, several techniques have been implemented to address this list of outstanding challenges in the 60-year history. For example, spatial compounding has been implemented to smooth out that speckled texture appearance. Doppler imaging can be used to enhance visualization of blood flow to determine vessel locations, which could also be an interesting approach to vessel segmentation. Harmonic imaging reduces clutter, but unfortunately does not work uniformly for all patients, particularly patients who are overweight or obese. Then we have a method that I developed during my PhD, a coherence-based approach to imaging, which is effective at reducing clutter in cases where harmonic imaging fails, as shown here in this image on the right of a beating heart, which is processed using a different approach from the process on the left, but they both use the same raw data. We can also image the mechanical properties of tissue to distinguish stiff tumors from surrounding fat, which enables tumor segmentation. Other techniques also exist to provide similar benefits to those summarized here. However, none of the advances summarized on this slide simultaneously address the long list of outstanding challenges in the 60-year history of ultrasound, yet they all rely on the same raw ultrasound data to make images. In addition, some of the advanced methods, like the coherence-based method, are computationally intensive and have yet to be implemented commercially as a result, despite the clear benefits that you see. So I believe that this requires us to rethink the image formation process to determine if we can address multiple challenges in a single step and with computational efficiency. This is what motivates me to explore deep learning as a single solution. Our goal is to transform noisy, poor contrast images that suffer from attenuation at deeper depths, as shown here, into a desired image that only displays a structure of interest, such as a needle tip. We can then also display this needle tip by itself if desired. I then want to add to this network another network that transforms noisy, poor contrast ultrasound images into a desired image that only displays a structure or target of interest. Then I can add the result from the previous slide to show where the needle tip is located in relationship to this structure of interest. This concept is the topic of my Trailblazer Award from the NIH. At the time that I applied for this award, no one was thinking in this direction. So my group is one of the first in the world to get this field started, this merger of ultrasound image formation and deep learning. Successfully implementing the proposed concepts would be a significant improvement over the current state of the field and would overcome many of the long-standing challenges with poor image quality in a single image formation step. So you've seen two examples of some of our exciting work on an original and novel idea. And to explain this idea in more detail, I assume the audience is well-versed in deep learning principles. So I'll tell you more about ultrasound, starting with a primer on beamforming. Then I'll transition into how we're using the concept of beamforming, merging it with deep learning to detect both sources and targets, such as biopsy targets. And I'll end with a summary and outlook. Let's think about beamforming and where it fits into the overall ultrasound system architecture, which has three components. The first is a scanner, which houses much of the electrical and computing hardware of the system. The second is an ultrasound probe that has an array of different shapes and sizes and is used to interface with the body to make images. The third is a monitor that displays the images on the screen. The way that these three components interact is that the scanner transmits electrical pulses to the ultrasound probe, which contains an array of piezoelectric elements that convert the electrical signals into mechanical pressure waves that are propagated throughout the body. These pressure waves reflect off of different structures in the body and return echoes to the probe that convert the mechanical pressure echoes into electrical signals that are sent to the scanner, which receives the echo signals, sends them to an onboard computer for processing. And this is where beamforming comes in. You can think of beamforming as the first line of software defense against a poor quality image. After beamforming, the signals undergo some more post-processing, such as scan conversion, log compression, and filtering, and finally the image is ready for display on the monitor. So now let's take a closer look at beamforming and why it's needed. Here we see the internal components of a standard ultrasound probe that has an array of piezoelectric elements shown in blue, and these are the elements that transmit sound into the body. If we consider the shape of the ultrasound beam produced by these elements, ideally, we want it to look like this, a constant, infinitely narrow beam. However, due to the physics of sound propagation from these elements, we instead get something that looks like this, a broad, unfocused beam that increases with depth as the beam travels into the body. So we use beamforming to shape our beam to give us something that looks ideal at a specific focal depth. So now we have the ultrasound probe that is interfaced with the body, and we make focused transmit beams and transmit them one at a time at fixed locations across the aperture. With each transmission, we receive the echoes and process the received signals to build an image line by line. Just like we can shape our beam on transmission, we can apply the same concept to shape the energy distribution of the received signals for each line in the image. And this is the process called receive beamforming, which we'll focus on throughout the remainder of this presentation. If we want to image a needle tip after the transmission of sound, there are a host of challenges introduced with ultrasound imaging. For example, resolution challenges exist because the beam width grows with depth. So in my lab, we're exploring alternative methods to simplify the task of needle tip detection by replacing sound transmission with light transmission. And we call this replacement photoacoustic imaging, or PA imaging. To perform photoacoustic imaging, we add a laser to our ultrasound imaging system. Our target of interest is the needle tip, and we need a way to transmit laser light toward this target so it can absorb the light, undergo thermal expansion, and generate a sound wave that we can detect with a conventional ultrasound transducer. After sound detection, everything here that follows is very similar to the ultrasound image process, where the array of piezoelectric elements convert the mechanical pressure waves into electrical signals that are sent to the scanner, which receives the signals, sends them to an onboard computer for processing. Again, we see this critical beamforming step, then some more post-processing, and finally, the photoacoustic image is ready for display on the monitor. The nice thing about photoacoustic imaging being ultrasound imaging with a laser is that we can interleave ultrasound and photoacoustic images to improve the clinical experience. Let's put this all together by looking at a simulation of an ultrasound wave from a point source, which could represent a photoacoustic signal from a needle tip. This wave propagates outward spherically toward the ultrasound receiver. The signals sensed are then displayed in a format shown here, known as channel data. Our goal is to convert this channel data into an image that looks like the source that created it. However, when we apply today's beamforming methods, we don't get this nice reconstruction. Instead, we get something like this, where the shape is distorted, it appears at an incorrect depth, and there are artifacts to the left and right. One reason these deviations exist is because of a fundamental flaw with current beamformers. They make assumptions about wave propagation that are not always true. For example, the time t that it takes to receive the signals related to a depth d of the point source, they're proportional to each other through the speed of sound. We assume that the speed of sound c is constant, but it is not constant when there are multiple tissue layers with varying sound speeds. So we have artifacts being produced when the acoustic environment significantly deviates from our assumptions, not only assumptions about constant sound speed, but also incorrect assumptions about constant density or the absence of multipath reverberations, as well as incorrect assumptions about the absence of acoustic reflections. Let's take a closer look at what happens when there are acoustic reflections from a point source propagating outward spherically. It encounters a reflector and a second wavefront is produced, giving us channel data that looks like what you see on the far left. When we beamform the signals in the red box, we get the image on the right. The effect of reflections is easier to appreciate when there is a single point source for either ultrasound or photoacoustic imaging. The wavefronts then become more complicated when there are multiple scatterers in ultrasound imaging, but the same principles apply. Basically, that the underlying signal looks considerably different in the presence of reflection artifacts for both single point sources and multiple ultrasound scatterers, which can be thought of as multiple point sources. So we can think of artifacts as the mapping of signal sources to the wrong location. Our goal with deep learning is to map signal sources to the correct location, where we input raw channel data like what you saw on the previous slide, pass it through a well-trained network, and then use the output of the network to create images from the learned parameters. We're training our algorithm with simulations of ultrasound or photoacoustic wave propagation. And what exactly are we learning? Well, we can appreciate from the photoacoustic point source simulations that sources that are closer to the receiver will have a different wavefront shape than sources that are farther away. So there should be a unique curvature and shape of the wavefront for each depth. And we believe we are learning the unique shape to depth relationship for photoacoustic point sources, whereas all other wavefronts are expected to be artifacts. And a similar concept applies to ultrasound data if we think of scatterers as multiple point sources. Now let's think about these concepts within the context of a clinical application, specifically the application of ultrasound-guided biopsy, where the goal is to insert a needle under ultrasound guidance to remove tissue for examination under a microscope. We need to see the needle tip in the ultrasound image for this to be successful. Some patients produce very nice images of the needle tip, as shown on the left, other patients not so much. We want to have a more uniformly distributed approach to tell us where that needle tip is located for all patients, regardless of the patient being overweight or obese. And we can do this by inserting an optical fiber into the hollow core of the biopsy needle and producing photoacoustic images that would be overlaid on the ultrasound images. We can then expand this concept and attach a robot arm to our ultrasound probe to relieve the operator from searching for that tiny photoacoustic signal during the biopsy procedure. We tested this concept in the controlled experimental environment shown here, where we have an optical fiber inserted into the hollow core of a needle and rigidly attached to a translation stage. I'm about to show you a video demonstration of this robotic system in action, where the needle is advanced into tissue and the ultrasound probe held by the robot is making subtle motions to stay centered on the needle tip. We can then overtake the robot if we're nowhere near our biopsy target, search for the target, find it, and then release, and it's the robot's job to find that needle tip. If we transition to a view of what we see on the monitor, we see photoacoustic images on the right and a segmentation of the photoacoustic images on the left with the green line representing the center. Initially, there's poor SNR and the system has difficulty finding that needle tip. But eventually, the signal with the highest SNR, or the signal-to-noise ratio, is confidently centered in the image. From this demonstration, we can appreciate that artifacts are problematic not only for us as humans interpreting images, but also for robots that are relying on these images to determine where to go next. And this is one additional motivation for our deep learning approach to image formation. To explore our deep learning approach, several networks were tested as listed here. The next few slides will describe our results with the faster RCNN approach published in IEEE Transactions on Medical Imaging in 2018, which is one of the most highly regarded journals for medical imaging in our field. The network architecture takes channel data as an input and has three outputs. The first is a classifier of a detected wavefront as a source or an artifact. The second is a confidence score, and the third is a bounding box location. While training the networks, we can vary multiple parameters, and one of those parameters is the noise levels, where we can start with no noise or a noiseless case, as shown in the bottom left, and then add increasing levels of channel noise to increasingly challenge the system. The bar graph on the top shows source and artifact classification accuracy in shades of blue as a function of the noise level, which is listed on the x-axis. We see perfect classification accuracy in the noiseless case and in the negative 3 dB channel SNR case, and then accuracy starts to degrade as noise increases. However, what is remarkable about this result is that we have greater than 82% classification accuracy at a channel SNR of negative 15 dB. But when you and I look at the images created with this level of noise, it is difficult for us to see where the sources and artifacts are located. So it's remarkable that the network is able to detect anything. Then as the noise level increases, the accuracy of classification plummets, and there are more missed sources and missed artifacts, which are shown in shades of yellow. The ROC curves on the right show the same trend for both sources on the top and artifacts on the bottom. Essentially, we achieve perfect classification accuracy for the noiseless case, and then the classification performance starts to degrade as the ROC curves transition farther away from the ideal curve as noise increases. We can also use our network output to measure the location accuracy of our bounding box detections, where the x-axis of these plots show the same noise levels from before, and the y-axis shows our location error when comparing the output location of the bounding box to the known location from how we input and train our simulations. That would be the ground truth. We have a mean absolute error of about 0.1 to 0.2 millimeters in the axial and lateral image dimensions. This result is nice because it shows us that our location error is within the resolution of the imaging system. So it's within our ability to resolve a single target. There were other parameters that were varied that I don't have time to get into, but those parameters were the number of sources and artifacts, the sound speed of the imaging environment, and the acoustic receiver model. Once we had enough variation, we were able to test our networks on real experimental data. And we did that with this controlled setup shown here, where we have 4 point-like sources when the probe is placed in the orientation shown. We can then selectively illuminate the number of sources that should show up in our image. So the photograph shows us selectively illuminating 2 sources, and the channel data on the far right shows the results of what happens when we selectively illuminated 3 sources. Zooming in on this result, we see 4 wavefronts, although only 3 sources were illuminated, so there should only be 3 sources in the image, meaning that one of these wavefronts is associated with an artifact. When we apply today's beamforming methods, it looks as if there are 4 sources, which could cause confusion for a clinician that is relying on this image to make a treatment plan. So we want to eliminate this confusion by returning to the raw data that created this image and passing it through our deep learning network to create a new kind of photoacoustic image that we call our CNN-based image. This image has 3 features. There are no artifacts, simply because we choose not to display anything that the network identifies as an artifact. The sources that are displayed have high contrast because we set the amplitude with which we display anything the network detects as a source. And we also have high resolution at depth because the size with which we display the source is related to the location errors that you saw on the previous slide. And these location errors are fairly consistent across depth, just as they were consistent across varying noise levels. Here's a great example showing why our excellent resolution as a function of depth is beneficial for a real preclinical case of a cardiac catheterization procedure, where the goal is to thread a catheter from the femoral vein in the leg up toward the heart in order to administer treatment for heart disease. We can perform photoacoustic imaging as the catheter is being guided toward the heart by inserting an optical fiber into the hollow core of a cardiac catheter, similar to the way we insert an optical fiber into a needle for biopsy guidance. In both applications, The tip of either the catheter or the needle is intended to create a point-like source. When we beamform the raw data with traditional beamforming methods, we get the images that you see on the far left. Although the image should contain a point-like source indicating the catheter tip location, we can't see a point-like source because the resolution is so poor at a depth of about 8 centimeters. So we want to return to the raw data that created the traditional beamformed image, pass it through our well-trained network, and you see some example bounding box detections from this network shown on the second panel. We can then use the outputs of the network to create a CNN-based image, which clearly shows where the catheter tip is located. We can then learn something from the CNN-based images by overlaying them on the traditional images to determine exactly where the traditional image was trying to tell us where the catheter tip was located. The previous result was in the vein, and our goal is to guide the catheter from the vein to the heart. Now, these cardiac catheter tips are typically tracked by fluoroscopy during this interventional procedure to provide some visualization and guidance. And you see example fluoroscopy images here, which suffer from two limitations. One is that these images don't provide the same depth information that you saw on the previous slide. The second limitation is that it utilizes harmful ionizing radiation, which can be detrimental to the patient with multiple repeated usage, and also detrimental to the doctors and clinicians operating on patient after patient, day after day. While ultrasound is widely available and it can show us how deep the catheter tip is located from the body's surface, ultrasound has a failure point because the catheter tip blends into the background when it touches tissue, as you see on the bottom panel. When we switch to the photoacoustic imaging mode, which was obtained by inserting an optical fiber into the hollow core of the cardiac catheter, we get this very exciting result that you see on the right, showing that we can see the cardiac catheter tip in the in vivo photoacoustic images from the heart, regardless of tissue contact, and without requiring ionizing radiation. This result implies that we can potentially use photoacoustic imaging to replace fluoroscopy. So we saw how we can detect point sources in several examples. Now let's transition to how we can detect a biopsy target. First, we would want to attach the robot to the ultrasound probe as shown previously, and then we want to deliver fast, real-time updates of the biopsy target. And ideally, this entire process would be automated so we don't have to overtake the robot to find the biopsy target. Now, plane wave imaging is one of the fastest techniques available to achieve this goal for ultrasound imaging. To compare plane wave to focused imaging, which I talked about earlier, for focused imaging, we would transmit in groups of elements one at a time to build an image line by line. But with plane wave imaging, we would transmit on all elements at once. We don't typically use plane wave imaging because the quality is poor when there's just a single plane wave. But we like it for this approach, at least for exploration of this idea, because it's fast. We trained networks with simulations that mimic the physics of ultrasound wave propagation. We reduced our problem to detecting a single cyst in tissue, and the cyst could either be anechoic, meaning it does not return any echo, so it should appear completely black in the ultrasound image, or hypoechoic cyst, meaning that the echoes returned have a lower amplitude than the surrounding tissue. We limit our transmission to a single plane wave and a single insonification angle when creating the simulations for training our networks. We also have multiple simulation parameters that were varied as shown here. To provide a graphical representation of these parameters that were varied and the step sizes that were varied, we essentially expanded our target diameter and we varied the location of the cyst. We also varied the speed of sound surrounding the cyst. After training the network with these multiple possible variations, we were ready to test it, so we created an additional test set as described here, which has 100 additional examples that were not included during training and randomly chosen contrasts ranging from anywhere between an anechoic cyst to a hypoechoic cyst with -6 dB contrast. Here is an example of the process for testing. We start with a ground truth known location of cis, use this ground truth to create simulated raw channel data. From the simulated raw channel data, apply the mathematical component of image formation to get this beamformed image. You can see that the cyst is located somewhere in the top left corner, but it's plagued by acoustic clutter and you can't really see the cyst very clearly. So we want to return to the raw data that created this beamformed image, pass it through our trained network, and get an output that we call our CNN-based image that shows us very clearly where the cyst is located, simply because we train with the ground truth rather than using the image formation process. If we compare the CNN-based image to the ground truth, we have a high dice similarity coefficient of 0.98. We're now ready to transfer this network to experimental data. And we do this for automated acquisitions across an experimental phantom, where the robot is attached to the ultrasound probe and it's swept across the phantom surface in order to focus on two targets that you see in the B mode image on the bottom left. One target is easier to detect than the other, and when we apply basic thresholding, we see exactly that. We see that not only is the target in the front easier to detect, but the target in the back is harder to detect and also has some frames where the target simply cannot be detected because there are just some skimped frames with no detections. We also see that for both of these cases, the threshold approach overestimates the cyst size when you compare the green region to the black region, which is the ground truth known cyst size. With the DNN approach, these errors are remedied. Particularly, the cyst size is more similar to the known ground truth, and there are less frames with missed detections. Now, the image on the previous slide was not completely perfect, so we studied the performance as a function of radius to illuminate why this is the case. And we see from these simulation results already that the network performance degrades as the cyst size gets smaller and smaller, where network performance is defined as our dissimilarity coefficients. We can then bin our simulation results in integer multiples of radius to get a mean and standard deviation to more clearly elucidate this trend. And then when we compare to the phantom result from the previous slide, we see exactly why the results were not that great. Simply because our simulation results were not that great, so we're not able to do better than our simulations. This means that we need to think about how we can redesign our network to produce better results during training. One thing that we thought about was how can we possibly include more features to improve those small cyst errors? And this is what led us to a GAN approach, where we wanted to not only output segmentation results, but also mimic the generation of an image. So we get a DNN image and a DNN segmentation, with the goal being that the network is forced to only produce segmentations that are meaningful if the DNN image is a true representation of the beamformed image. So this was our idea to include more features to improve small cyst errors. And in doing so, we were able to take a step back and realize that this network offered us the opportunity to combine both image formation and image segmentation in a single step. And so taking this idea and running with it, we were ready to transfer to experimental data after a few more network updates. One of the network updates was that we realized we didn't need to use a GAN, so we got rid of our discriminator. It was easier to train that way. We were also able to change the type of data we were using. So before we were using radio frequency or RF data, and then we switched to the IQ data from the system, which allowed us to downsample more vigorously and pass more data through our network at any given time. We also were able to apply more tuning to our network, and then we get these two outputs highlighted by the black rectangles. One is a DNN image and the other is a DNN segmentation. And you can compare those two outputs to the ground truths shown to the left of the rectangles. We also see that we get not only two benefits in one, but actually four benefits in one, with the third benefit being reduction of clutter. If you look at the DNN image, notice how black that cyst appears in comparison to the beamformed image. The cyst should be black because it's an anechoic cyst and it should not contain any internal echoes. So we were able to get rid of that acoustic clutter that was making it appear as if there were signals within the cyst. The fourth output is obtained by the smoothness that you see in the DNN image. So this mimics the spatial compounding effect that is one of the advances over the 60-year history of ultrasound imaging. Now, the ultimate test of these networks is to determine how well they perform on patient data. Here is an example result from our recent publication answering this inquiry. You see that the DNN image on the top has smooth speckle texture, and it also has a segmentation of the cyst that looks very similar to the ground truth, which is shown to the far right. The DNN image also has reduced clutter in addition to smoothing out the speckle texture, which you can appreciate by comparing it to the ground truth beamformed image shown at the top. These results are remarkable because it shows us that this one network architecture that you see in front of you and which is described in more detail in the publication below, this one network architecture can produce multiple outputs with important information for biopsy guidance and automation based on ultrasound images alone. And particularly, the input to the network was this one single raw data that's producing these multiple outputs. If we expand the image field of view a bit more and now include focused transmissions, we see immediately that we have better image quality, as you see on the far left. We also see that speckle returns. Some clinicians like the speckle because it helps them to detect different features. So there may be some cases where we want to get rid of speckle, and there may be some cases where we want to preserve it, especially for human observers. The take-home message here is that we're able to improve upon our initial network to reduce false positives with this expanded field of view, where the false positives are shown in red. They're the network detection overlay in comparison to the ground truth. CysNet1 was our original network, and CysNet2 shows the reduction of false positives. CysNet2 was trained to include, or was trained with the inclusion of more features such as now lines and point targets, not just cysts as initially trained. So we see that there are multiple outputs and ways that we can present the output to the clinician based on a desired task. These results are very encouraging, and it shows us that we can have multiple outputs all starting from the same raw data. Taking a broader perspective, many groups around the world are starting with raw ultrasound data now and outputting multiple types of image information as shown on the far left column. Here is where we fit into the bigger picture. And our work differs from these other approaches because we take the raw plane wave data from a single transmit. And we also show that we can take focus data now. And we more recently showed that we can not only produce the segmentation map, but also a matching B-mode image from the single input of raw data, whether it's focused or plane wave data. Although this graph is a snapshot of the initial advances in this area up until last year, 2019, when searching the literature for 2020, it is apparent that the number of ideas and contributors to this field is growing exponentially. As a result, I believe we are entering a new age of ultrasound image formation that relies on deep learning. Switching gears a bit to another approach that can be used to detect biopsy targets for potential concatenation with any one of the previous networks that we've been discussing, let's talk now about this method that I developed for my PhD dissertation, which is called short lag spatial coherence imaging. This method is very computationally intensive because of a step in the middle that requires coherence calculations, which relies on multiple cross-correlation steps. This led me to question, can we simplify or speed up this process by replacing the correlation calculations with a deep learning approach? And this is what led us to design the CoherNet architecture shown here, and it basically fits right into the pipeline of image formation for the coherence-based images. Here are some examples of the DNN approach on the right and the original approach on the left. If you're trying to find a difference but cannot, that's because there is very minimal difference. In fact, the image-to-image correlation is as high as 0.93 for all test cases. This network also achieved our original goal of speeding up our ability to produce these images. The network processes images at a speed of 3.4 times faster than the original algorithm that contains many coherence calculations. In conclusion, we can appreciate that both ultrasound and photoacoustic images can be presented in novel formats that extract information directly from raw channel data with assistance from deep learning. This allows us to have a one-step approach to address historical challenges with image quality, combining multiple benefits and outputs in one. Our initial results and those of other groups around the world also highlight capabilities of deep learning for image formation and for speeding up the delivery of images with more advanced beamforming methods. This approach is also promising for autonomous robotic tracking tasks. A few final plugs. The first is for this challenge that I created for ultrasound beamforming with deep learning. The challenge is now closed, but I pointed out here because we have a lot of useful resources for anyone wishing to enter this space and benchmark their enter this space and benchmark their methods against the challenge winners. So if we return to what I call a roadmap of some of the major advances in ultrasound imaging, my outlook is that deep learning is now starting to be the next frontier. Although it's starting to be the next frontier, what we see is that a lot of the known challenges with deep learning still persist. We need training sets that include multiple possible variations that we can expect from patient to patient. We also need networks that are generalizable across multiple ultrasound or photoacoustic imaging system types, multiple target sizes and target shapes, and the list goes on. We also want to be able to interpret networks to understand why they're outputting what they output. We know the domain of network interpretability is an important area in deep learning in general, and this importance similarly translates to ultrasound image formation. I've also noticed that the evaluation metrics that are chosen must be tied to a specific imaging task. You've seen us use dissimilarity coefficient, image-to-image correlations, as well as speed to quantify how well our networks are doing. A lot of these different parameters are some of the useful resources that came out of the Kubdal Challenge, and so I invite anyone working in this space to visit the website and help us as a field to have more standard metrics for comparison and benchmarking. I've also shown you that it is possible to have multiple outputs from a single input. And I challenge anyone working in this space to think about what else we can combine and how useful it would be to have one input and multiple output formats that a clinician or sonographer can view to make a more informed and more accurate diagnosis. Finally, there is also this special issue of IEEE Transactions on Ultrasonic Ferroelectric and Frequency Control published this month, December 2020. My co-guest editors and I took great care to summarize the 17 articles published in this special issue, so I invite you to check out our guest editorial that contains this summary. Finally, I would be remiss to end without saying thanks to my dedicated team of students and collaborators who have helped to make all of this possible. Thanks to my funding sources for supporting this work. Visit my lab website, pulselab.jhu.edu, to learn more, and follow me on Twitter for real-time updates of our work. Thank you.
Thank you, Dr. Bell, for that interesting talk. Our last speaker for this meetup, Dr. Shayoni Datta, is a senior application engineering at Mathworks and focuses on technical computing. Her core experience lies in computational biology models and simulation, advanced statistics, machine learning, deep learning, medical imaging, and clinical trial analytics. She has a PhD in computational biology from Indian Institute of Technology, Delhi. She has published and reviewed papers in numerous international conferences and journals. Welcome, Dr. Shayoni Datta, and it is over to you.
Well, let's talk about some predictive models for time series signals today. I, Dr. Shayani Datta, a senior application engineer specializing mostly in data sciences and computational biology, would walk you through few of these deep learning and machine learning models that you can actually use for time series data, and that too mostly signals. So how do engineers address these challenges to develop effective deep learning systems able to solve real world problems? Let that be our leading question in this short talk today. Even though I don't have a strong background in signal processing, I've developed a keen interest of late in it. And you will notice that this session keeps a specific focus on signal processing applications. Arguably, this will be even more useful to understand the key role played by data in real-world deep learning problems. The first response you would get back from most people, and easily what most people would expect to hear back, would be a statement on the type of deep learning network used, like this one, a bidirectional LSTM network with layers of 150 hidden units, each followed by one fully connected layer and a softmax layer. However, if you ask me, I would also say a lot of data, a good dose of signal processing expertise, and the right tools for the specific application in hand. The difference between, I repeat, between those two responses is not trivial. Now, one of the most common architectures is a convolutional network, or CNN, that consists of a deep stack of hidden layers that work with feature extractors that automatically uncover the hidden patterns and low-level information from the data set. There's also this idea of recurrence in neural networks that help in retaining information that the layers in the network have learned over a period of time. An LSTM contains a memory cell that consists of gates that decide whether information is to be kept or removed. In other words, the network can preserve information learned from the data throughout the time. Although in a small minority of signal-related publications, networks are directly fed raw data. In the vast majority of cases, you will find some form of data processing before feeding the signals into the network. For example, time frequency transformation are often used to convert signals into image-like representations to use network architectures similar to those used for computer vision applications that is often the case of CNN. On the other hand, with LSTM networks, it is common to extract time-varying features from the raw signals in order to lower the data rate and consequently the complexity of the network and the learning process. Let's get into specifics of what I'm talking about. When I talk about deep learning workflow or machine learning workflow, a simplified view results in four main stages. Data prep, obviously, algorithms and modeling, simulation and testing, and ultimately deployment into the field. I'll try walking you through all four parts of the workflow, talk about some of the challenges that you may face with each of them, and point out how Matlab can make it all come together efficiently and effectively to deliver value to you. Data preparation and management turns out to be one of the most critical ingredients to success, and it's really, really hard. Trust me. Today, data comes from multiple sensors and databases, structured or unstructured, spanning time with different time intervals, noisy or from different domains, and so forth. The data needs to be prepared for the next stage, which is the algorithms and modeling stage, and it is definitely time consuming. A great proof point, Andrej Karpathy talked about this in 2018 while doing his PhD work at Stanford. He did not need to spend much time on the data. He was doing research and focused almost exclusively on creating new AI algorithms. But as director of AI at Tesla, he spent 3/4 of his time on the data because now he's building the car, not a better performing predictor anymore. You will find that you end up in the same situation most of the time, spending an enormous amount of time inside the data. Matlab and Simulink can make that time more effective and more productive. So let's look at the whole workflow in more detail, like probably signal processing, where you'll need to do signal labeling for data preparation, train a network, evaluate the performance. If the performance isn't great, go ahead, augment and add features, and eventually do code gen for deployment. So let's specifically look at signal labeling today. And it's beyond just data manipulation, Data labeling is required for any kind of supervised learning algorithm, and this can be time consuming and error prone. For deep learning, Matlab provides data labeling apps like the Signal Labeler app that enables you to label signals for analysis or for use in machine learning and deep learning applications, extremely making life easy for you. We have other labeling apps too, all of which can generate code for you. Let's move on to the second step in the workflow, the one that perhaps gets the most attention always, the AI-based algorithms and models. So within the Matlab environment, you have direct access to common algorithms used for classification and prediction, from regression to deep networks to clustering. And with Matlab, you can easily use pre-built models developed by the broader community, such as FastNet50 for classification or YOLO for object recognition. While algorithms and pre-built models are a good start, it's obviously not enough. Examples are the way engineers learn to use algorithms and find the best approach for the specific problem. We provide a host of examples for building deep learning models in a wide range of domains. And if you actually go and see, we have more than 200 of them for deep learning. I've mentioned about apps for data preparation, like the Signal Labeler. We also provide apps for modeling. For deep learning, we ship pre-built apps that help automate the training steps and provide visualizations for understanding and editing deep learning networks. We have Deep Network Designer, where you can access pre-trained models, like Sweetlet over here, visualize an important model, change the properties, create a model from scratch by using the libraries, connect them, auto-arrange, analyze to find if there are errors or not. Then you can import data into it and go ahead with training by changing the training options, choosing the solver type, initial learn rate, and eventually, once you start training the network, you can see the accuracy and loss in real time. Choose to stop, go back, change a few settings, and eventually export and generate code for the thing. In the latest release, there is now an app to manage experiments. Here's a short overview video highlighting its capabilities, where you can explore hyperparameters, monitor training progress, define experiments with Matlab code, keep track of your work, and export model results. So over here, you can actually go ahead and define experiments with Matlab code and change or monitor your training progress. You can actually export the train network over here and have them run. Okay, so the electrical activity in human heart can be measured in sequence of amplitudes away from a baseline signal. For a single normal heartbeat cycle, the ECG signal can be divided into the following beat morphologies, like all of you would know about this, right? Like C wave has small deflection before the QRS complex, representing atrial depolarization. The QRS complex, has the largest amplitude portion of the heartbeat. And the T wave, a small deflection after the QRS complex, representing ventricular repolarization. Even previously I never knew about hormones, but recently, since I've actually gone through multiple ECGs, I've always want to dig deeper and understand what all of them mean. And it's really interesting if we go ahead and do that. So ideally, let's get back to the problem. The segmentation of these regions of ECG waveforms can provide the basis for measurements useful for assessing the overall health of the human heart and presence of abnormalities. Manually annotating each region of the ECG, imagine. Each region of the ECG signal can be a tedious and time-consuming task, obviously, right? Signal processing and deep learning methods potentially can help streamline and automate regions of interest annotation. Isn't that really cool? This example uses ECG signals from the publicly available QT database. The data consists of roughly, 15 minutes of ECG recordings with around a sample rate of 250 Hz, measured from a total of, around 105 patients, not 9. Okay. To obtain each recording, the examiner placed 2 electrodes on different locations on a patient's chest, resulting in a 2-channel signal over here. The database provides signal regions labeled generated by an automated export system. In fact, in this example, you can use deep learning solutions to provide a label for every ECG signal sample according to the region where the sample is located. This process of labeling regions of interest across a signal is actually referred to as waveform segmentation. To train a deep neural network to classify signal regions, you can actually go ahead and use something like LSTM, long short-term memory network. In fact, over here in this example, it shows how signal processing or in fact pre-processing techniques and time frequency analysis can be used to improve LSTM segmentation performances, in fact. In particular, the example uses Fourier single squeeze transform to represent the non-stationary behavior of the ECG signal. And let's actually look how this actually helps you. So going back to the workflow that you were talking about, where we had signal labeling, which we actually looked into in terms of data pre-processing, then coming to the second step where we're building AI models, you want to train a model, evaluate the performance, and we just saw, we had some sort of performance in terms of doing the segmentation of the ECG signals. And probably the performance wasn't great, so the intent would be to probably augment the data or add new features to improve the accuracy of the segmentation, right? So ideally, this can actually give you an idea about how extracting different features can improve the accuracy of the segmentation. So training deep networks with time domain signals most often require extracting relevant features. And you can actually see that, the true class and the predicted class for QRS, in case of raw signals, is as good as 61.4%. The filter signals were slightly higher, around 73%. And with Fourier single squeeze transform, this is amazing. It's around 90.7%. So I think the QRS region is getting segmented well. And I think it's even for the P and T waves also, that it keeps increasing with the Fourier single squeeze transform. So over here, the emphasis is again on extracting relevant features and a little bit of pre-processing that the signals require before, you realize how well the accuracy is going to be effective. So when extracting features from signals, it is very common to first organize signals in buffers or frames which could be overlapping between them to get better time resolution. A large group of feature extraction techniques, also known as time frequency transformations, is based upon transforming each of those buffers in the frequency domain via an FFT or a similar operation. The simplest type of output that you get this way would be called short-term Fourier transform or STFC, and also spectrograms. You find these used very often with network sites that were originally designed to work with images, since these 2D signal representations look indeed a lot like images. When working with speech or other audible signals, you tend to see more advanced types of spectrograms with frequency scaled and reorganized, more in line with human perception, obviously. These representations are more compact while keeping a good level of perceptual detail. So for our trigger word detection example, we've used yet another approach that required yet a few more computational steps. The resulting features, which are very common for speech and audio problems, are called MFCC, a shorthand for Mel frequency septal coefficient. These and many other commonly used features are already available as Matlab functions these days, so you don't really have to implement these steps yourself and worry about matching exactly what others have used. Even if you were only interested in, I would say, just time frequency transform, there would be plenty of different options available. For example, I would say wavelength-based techniques are well known to deliver better time resolution, or constant Q transforms is another example of perceptually relevant representation widely found in research publications. On the actual feature side, the spectrum of possibilities is quite wide, actually. For example, wavelength scattering, listed on the bottom left, is one of the so-called invariant space methods, and it can be seen as a way of applying some convolutional returning layers to your signals without having to manually train those layers. Interesting, isn't it? And there obviously is much more available across the different Matlab toolboxes. So going back to that wavelength scattering technique, compared to extracting a set of known features or transforming a signal into time frequency domain, it would actually let a network do it completely on its own. I actually find this like magic, but it isn't really. You may have noticed that we haven't even at all presented that as an option initially. The reason is that, with a few notable exceptions, that hasn't yet worked well, because especially at high sample rates, signals still require too much learning from deep learning systems. That would translate to too complex networks and too much data. There is an approach that is often considered as a type of feature extraction that's worth mentioning here. Consider a multi-layer convolutional network, and suppose you are already able to demonstrate that, no matter what, in order to extract meaningful understanding. For example, to derive the same information from different manifestations of the same type of event, ideally, you would always need to learn through your first set of network layers to transform your signals always in the same way or extract the same set of features. In that case, instead of learning those weights from the scratch, as in a convolutional neural network, you may just as well decide to use your own fixed weights. Wow, that's interesting, isn't it? This approach has been investigated by several authors and research and often referred to with names such as wavelength scattering or invariant scattering convolution network. You can think about this as a deep feature extraction approach, at least. It can help relieve requirement on learning complexity and data set size, and is available in Matlab as a package framework for feature extraction. So the first layer essentially performs an averaging operation but loses the details. The second layer captures the details similar to SIFC features. The third layer provides complementary information which improves the classification. Modulus is used as the nonlinearity operator. There are many signals which have the same Fourier spectrum but belong to different classes. Wavelength scattering is thus a deep convolutional network which cascades wavelet transforms and modulus operators. For a signal of length L, the output of a scattering transform is a set of m into n features, where n is typically a small number and length of each feature. N is significantly less than L, thereby achieving dimensionality reduction. The length of the invariant scale plays a key role over here. There are additional constraints imposed on the wavelet to fit into this framework. So for this reason, not all wavelets can be used in this framework. Currently, only analytic models satisfy many of the constraints imposed. The well-known orthogonal wavelets are not a great match, actually. Okay, so now that we've had an idea about the whole AI workflow, the reason would be that we've been using deep learning to get some sort of signal segmentation or classification. How about trying to think about how to use machine learning for a similar kind of classification problem for signals? The workflow would remain entirely same, but it would just increase one little thing where you have to actually go ahead and extract the relevant features, which is actually called feature engineering over here. So, you need to use the domain knowledge to create features for machine learning algorithms. You may need to go ahead and do some sort of feature transformation to reduce dimensionality, curse of dimensionality, I would say. And feature selection is very important that you don't end up with redundant set of features. So, for example, if you have some 400 features and you realize that only 100 of them are relevant, it's very important to be able to actually rank those features and pick up the most relevant ones. So you may end up using a few techniques like PCA for dimensional reduction or NCA for selecting relevant set of features, or go ahead and do some signal processing techniques like power spectral density, wavelets, etc. For images, it could be a different set of them. But it is important that you actually value what feature engineering over here can actually give you, right? So how do you go about extracting features from signals? For networks of lower complexity, or those, for example, that use LSTM layers, time frequency representations won't be the right approach. You want to feed those networks with time series, but at lower sample rates than those of the raw signals that come actually from the sensors over here. In these cases, it's common to use just scalar matrix computer over time. We refer to these as features, for example, individual matrix of the spectrum like bandwidth or center frequency, or peak positions or transition points when looking at the original signals over time. Generic approaches like these examples may find use across different applications. And you can actually also come back to using wavelet scattering for automated feature extraction. Suppose it's like super complex, you can again use what we already explained, the method to automatically extract features from your signals and then use the classifier after this. So hence you're able to use the machine learning algorithm by picking up the best set of features from the signals that you're interested in. Eventually, if you want to have an interestingly built, optimized ML model, you can go ahead and use something called AutoML. In a traditional machine learning workflow, we actually start with importing data, perform some pre-processing, extract features, actually build models, then integrate the model in a larger system and deploy to production. There are several parts of the ML workflow where we can leverage AutoML techniques. Most time-consuming is the iterative hyperparameter tuning and model selection, isn't it? And especially for signal applications, feature extraction, because identifying performance features requires domain knowledge. AutoML delivers optimized models in 3 steps as follows. Leveraging signal processing capabilities of the wavelet toolbox, you can use wavelet scattering to extract features for signals as well as image data. Wavelets are really good at modeling spikes and irregularities in your signals. The scattering framework decomposes the raw signal into various wavelet components, yielding an array of wavelet-based features without intervention from you. To either avoid overfitting or for deployment to memory and power-limited embedded systems, you apply feature selection to reduce hundreds of wavelet features to a few dozen highly performant ones. Many feature selection methods are available, and we found NCA and MaxRel, MinRel to work really well. Model optimization, challenging because many combinations of model hyperparameters have to be explored. Even random search might take a long time. We may end up using Bayesian optimization that actually picks the next most promising combination based on statistical model of the search space. The next important thing that would actually strike someone who's basically into this AI domain using deep learning models or machine learning models is interpretability. Why interpretability? With the exception of a few basic models, they are generally not easy to understand. I mean, everybody's talking about this fact that maybe these are black box models. The trade-off is more accurate models are typically less interpretable. Where black box models are actually problematic is that not acceptable by company guidelines or user preferences, build trust for users unfamiliar with machine learning, all things equal with models that looks at actually right evidence. So a lot of regulatory requirements for interpretability come up, like Europe's General Data Protection Regulation, GDPR, or potential macro-level risk for financial stability board for the Carter High cycle. Going back to the workflow in more detail, I would say, we are done with signal labeling, training networks, evaluating performance, actually also extracting the right set of features to improve the performance. If you remember the waveform segment where we use and the QR segmentation actually hides up to 190% accuracy rate. The last and most important part, I would say, because you don't want the model sitting in your system, you want to share it with people and you want it actually working in real time, is about code generation and deployment. So you need to scale up and deploy. Deep learning training can actually take a long time, and with our cloud support and third-party integration, you can move the training to the appropriate compute platform, be it a GPU, public cloud, private cloud, and so forth. The point is that a single model in Matlab can be moved to the appropriate compute platform, saving an enormous amount of development time and allowing you to leverage the right compute technology to accelerate training. We also know that broader deep learning community is incredibly active and prolific, and new models are coming out all the time because we support the ONNX standards, and you have access to those new models and can work with them within the Matlab environment. To summarize the modeling step within the Matlab environment, you can have access to all of the algorithms and methods used to develop models. Secondly, you can work with them at the code level or through an app, and eventually you can accelerate training to the appropriate compute platform and can actually engage with the AI community through open neural network exchange. So for deployment, we've got a unique code generation framework that is actually one of the best, I would say, that allows models developed in Matlab to be deployed anywhere, actually, without having to, here comes, be surprised, rewrite the original code. You don't need to rewrite the original code, okay? So this gives you the ability to test and deploy the entire system and not just the model itself. Matlab can generate native, optimized code for multiple frameworks. It gives you flexibility to deploy lightweight, low-power embedded devices, low-cost rapid prototyping boards such as Raspberry Pi, and edge-based IoT applications such as sensors and controllers on a machine in a factory. In fact, we have support for FPGAs as well. So I would like to conclude that, eventually, edge deployment puts strict limitations on the size and performance of the code. And you can go ahead and quantize network parameters to integrate with something called the Deep Network Quantizer app that we have, which enables you to do automatic calibration on data, quantization, and performance validation. So here we close the whole session. And the key takeaways I would say would be that it's important to understand the whole workflow, where you're trying to pre-process and get your data in shape, which is actually the most time-consuming part, where you're working to label the signals, and you can actually use the signal labeler app Then comes the most important part where you're actually talking about building the model. So train the model, evaluating the performance of the model, and if it's not really good, going ahead and adding data or extract the right set of features to improve the accuracy of the model actually is the key point over here, where you can actually delve deeper and understand a lot about time frequency representations or transforms and how they can actually bring about improvements in terms of the accuracy by enhancing the features that you're extracting. Or you can just even go ahead and use something that we spoke about, like the waveless scattering. And eventually, how you need to figure out the deployment. So here it goes, and I hope you've enjoyed the small session that we had today.
And that brings us to the end of this session. Thank you all for your attention and support. We again thank our expert speakers for their excellent sessions, and we also look forward to you joining us in the future for such interesting tech meetups. If you need more information on Matlab and Mathworks products for AI, machine learning, and deep learning, please visit mathworks.com or email me at sjohn@mathworks.com. Thank you again. Stay safe and goodbye.